Hi everyone, welcome back to my channel, and today we'll be talking about quantum computing. Quantum computing is probably going to be the next big breakthrough for computing. But what is it? And why do you need to know about it? And further, how far are we from having this in our daily lives? To understand quantum computing, we need to break things into bits. A normal bit that all classical phones and computers work on is basically a switch. It can either be on or off, and it is represented as either a 0 or a 1 inside a computer. By observing and manipulating these bits in certain fashion, we are able to make the computer do really complex tasks or repetitive tasks so that we can sit back and relax. And this has simplified our lives significantly. Okay, so if normal computers are that great, why do we even need a breakthrough in this technology? Is there something that normal computers can't do? In fact, there are a lot of such problems. One famous example is finding the factors of a large number that is a product of two prime numbers. This is such a difficult problem that a classical computer would take thousands and maybe even millions of years to find the factors of a large number. And in fact, this is the key principle behind encryption in the industry today. The data is encrypted using this big number, and to decrypt it, you need its two factors. Everybody knows that it'll take thousands of years to decrypt this data without having the factors readily available with the person. So people are not really afraid that somebody would be able to decrypt it. And if they were able to decrypt it after 1,000 years, none of this information would matter anyway. Now, to understand the beauty of quantum computing, we need to understand a few things about how quantum computers work. And those things are superposition, entanglement, and interference. So first of all, let's talk about superposition. Superposition is an interesting thing to wrap your head around. The normal bits that we hear about in the classical computer world can either be on or off. They can be 0 or 1. But a qubit works fundamentally different. In a qubit, there might be a 30% chance that you will observe it to be on and a 70% chance that you will observe it to be off. To understand why this is happening, you can try to think of it like this, that a qubit is not a very stable thing. You can think of it like this, that it is quickly oscillating between the on and off state, and the higher tendency that it has to oscillate towards the on state, the higher the chances are that you will observe the qubit to be on, and similarly for the off state. But this by itself doesn't seem all that useful. If you can't even reliably tell what your qubit is, whether it is on or off, what use it is to us? Well, that's where in comes interference. Now, interference, I think, is the coolest part of the quantum computing world. And to understand that, I'd like to draw an analogy from noise cancelling headphones. When you wear noise cancelling headphones, what happens is that the noise coming from the outside is picked up by the microphones that are put inside the headphone. It tries to figure out the waveform of this sound, let's call it the sound wave, and it tries to create an exactly opposite sound wave inside the headphone. Since these two waves are exactly opposite, they destroy each other and you are able to hear pure silence. This is what destructive interference is. To understand constructive interference, think of what happens when you switch on the hear everything mode that some headphones have. What happens there is that the things that are happening outside are able to be heard in an even more amplified fashion inside your headphone. So what's happening is that your headphone is picking up the audio that's coming from the outside and trying to create a sound wave that is exactly in phase with it, so that you can hear the outside sound magnified. This is constructive interference. Now, the coolest thing about quantum computers is that we can make quantum bits interfere. And the reason for that is that quantum bits are actually also represented using waveforms. Unlike our normal bits, which can be represented using zeros and ones, quantum bits are rather represented using waveforms. And we can make these qubits or these waveforms interfere with each other. Now, the basic principle behind using interference in quantum computing is this, that when we create a certain logic and a certain architecture of a quantum computer, we set it up in a certain fashion such that all the possible answers that are wrong will destructively interfere with each other and only the correct answers will constructively interfere with each other, so that what we finally see to be the state of the quantum computer remains to be just what the correct answer is supposed to be. Even at this point, since the quantum computer fundamentally works on probabilities and not on certain on and off states, there is a high chance that the constructive interference that you're observing is from the right answer, but there still is a low chance that you're observing an answer that is not the correct answer. So in order to make sure that you're observing the right answer, quantum problems are usually solved several times over on a quantum computer before scientists can be sure that they are observing the correct answers. However, one bit is usually not enough for complex problems, and this kind of brings us to the last part of it, that is entanglement. Quantum bits usually need to be entangled together so that we can represent huge forms of data, just the way we do it in classical computers. However, there is one big difference. In a classical computer, we are able to simply group multiple bits together to represent a higher amount of data. But in a qubit system, things work differently. Entanglement is not just logical grouping of qubits. It is actually a physical relationship between these bits, so that a change in one of the bits can affect the changes in other bits. The details of entanglement and how this actually works is a bit more complex, and it's a topic that we can't really go into for this video, but do let me know if it is something that you would like to know about in another video. Now, I know that all of this is incredibly confusing, and it is supposed to be. After all, it's the result of years of research from quantum physicists. And what makes matters worse is that you can't observe quantum effects on a day-to-day basis. You're only able to observe them inside a lab. So it does make it a bit hard to intuitively understand how quantum physics is working. But then again, maybe we just need to accept these things as the basic principle of how the universe works. Maybe it is just axiomatic in nature, just the way we take gravity and electrostatics and Newton's 3 laws of motions to be the basic laws of the universe. This also needs to be considered just as axiomatic in nature. But observing these effects brings us to the next point. When will it so happen that you are able to observe all of these effects in your own local premises? When will it so happen that we'll have quantum computers inside our pockets and on our desks? Well, the answer is I really don't know. And see, the reason for that is that to run a quantum computer, we need really pristine conditions, and as far as I can tell, they are only achievable inside a lab. Now, these pristine conditions, let me give you some example of what these conditions actually are like. We are talking absolute zero temperatures, protection from cosmic rays, protection from nearby heat sources, protection from other small near atomic sized particles that are going around all the time, protection from interference from nearby electronic devices. This is very hard to achieve inside a consumer environment. So yeah, it is quite difficult to create quantum computers that can be used by people on a day-to-day basis, and unless the technology fundamentally changes, it is going to remain that hard. However, that doesn't mean that you can't use these computers today. Companies like Microsoft and IBM have already made their clouds on quantum computers. You can go ahead and check their websites and you can see the several quantum offerings that they have. Of course, there are no consumer level applications for quantum computers yet, but if you are interested, you can get your hands dirty over there. Now, let's put aside for a second how difficult it is to have a quantum computer in our day-to-day devices, but hypothetically, let's assume that somehow we do have quantum computers in our mobile phones and our laptops. But then, would quantum computers be the next big thing? Will they be able to completely replace classical computers? And the answer to that is no. The reason for that is quantum computers are good enough only for problems that can harness the power of constructive and destructive interference. Not all problems are structured in a fashion that they can benefit from this interference-related properties. Those problems would be better off being solved on a classical computer, since they are cheap and easy to maintain and very convenient to work with. Having said that, maybe sometime in the future, we'll have CPUs, GPUs, and some QPUs, which can be quantum processing units, inside our devices. And they can work together in harmony to create results for us that we had never even imagined. One more thing that I'd like to mention is that quantum computers are still in their infancy. The largest one that I know has only 127 qubits. That is a very small number of qubits. And due to the pristine conditions that are required to run a quantum computer, it is difficult to scale these computers up as well. Researchers are actively trying to figure out how to scale up quantum computers better, and let's see, maybe in a few years we'll have a solution to that. Once quantum computers become abundantly available, we can expect to see tremendous research speed in cybersecurity, artificial intelligence, medicine, logistics, and some other fields that we can't even imagine. So this is a technology to be excited about. So that's all that I wanted to share about quantum computing today. If you think there's something that I missed, please mention that in the comments below. And thanks a lot for watching.